Hi guys, so today we're doing section 2.8, which deals with graphing linear inequalities in two variables. Our objectives are to find solutions to linear inequalities, graph linear inequalities in one variable, graph linear inequalities in two variables, and then graph absolute value inequalities. Most of this stuff is review from Algebra 1 again. And we'll just jump right in. I mean, most of this shouldn't really be new, maybe graphing absolute value inequalities. So let's talk about some vocab here. A linear inequality in two variables can be written in one of these forms. So basically it's standard form of a linear equation, except you've got less than or equal to, greater than or equal to. And then it says an ordered pair xy is a solution of a linear inequality if the inequality is true when you substitute the ordered pair into the inequality. So we're very familiar with this kind of stuff. The first example here, we're just finding one solution. We're determining if one ordered pair is a solution of a linear inequality. But that's actually not all the solutions of linear inequality, and we'll talk about that after this example. But the first most basic part is just determine if an ordered pair is a solution to an inequality. So let's look at that. I mean, this is again fairly much review for you. So this is an ordered pair xy, and to see if it's a solution to the inequality, you basically write down the inequality and then substitute x and y and see if the resulting statement is true. Okay, so if I substitute x and y here, I get 5 times 0 minus 2 times negative 4, and now it's a question basically, is this less than or equal to 6? So this is nothing, and this becomes positive 8. So is positive 8 less than or equals to 6? No, that's not true. Okay, so positive 8 is bigger or equals to 6, not less than or equals to 6. And so the answer here is this is not a solution. Okay, so this is not a solution. And basically all of these are the same. You substitute a point into your inequality and see whether it satisfies the inequality, whether it gives you a statement that's true. Okay, so let's try another one here. Again, you've got 5 times 2 minus 2 times 2. Is that less than or equals to 6? This is the question based on this inequality. Okay, and so if you solve this, you get 10 minus 4. Is that less than or equals to 6? You don't really have to go all the way with this. I think you can see that that's 6. I'll write it down in any case. 6 is less than or equals to 6. Is that true? Yes, 6 is equals to 6. It's the equals part here that satisfies this. So you say yes, this is a solution. Okay, and again, what's a solution? 2, 2, that ordered pair is a solution to this inequality. That's what we mean when we say solution. Okay, not solution. This ordered pair is not a solution to the original inequality. Okay, and so you can try these two by yourself. I'll let you deal with that. That's fairly simple. I think you're okay with that. All right. So basically, this is just determining if one ordered pair is a solution to the inequality. Like I said earlier, this is not all the solutions. This is only one solution. Okay. Actually, solutions to linear inequality in two variables are infinitely many. It's a region. Okay, it's a whole region on the coordinate plane, and we'll show you that right now. So this says the graph of a linear inequality in two variables is the set of all points in a coordinate plane that represent solutions. So normally when we graph a line, you have infinitely many solutions on the line, but for an inequality there are an entire region of solutions. Okay, so for this inequality here, the shaded area, all the points that fall into this shaded area are solutions. Okay, and so it's a little bit different from a line, just a linear equation, because the solutions to a linear equation are on the line, but these are an entire region, and if it's only greater than or less than, actually the boundary line of the region is not included in the solutions. So points on this line here would not be solutions to the linear inequality. But if it's greater than or equal or less than or equal and your line is solid, your solutions would include all the points on the line and also the points in the region, okay, where you shade it. So you have to understand that solutions to a linear inequality is a region and sometimes includes the points on the boundary line. So it's not just one ordered pair like we were doing in the previous example. That's just a test to see if a point is a solution to an inequality. Okay, so a little bit different there. Alright, so let's try and graph some. Basically this whole section deals with graphing. So let's graph some inequalities. Okay, so the first two in our example 2 here are just one variable inequalities. Now we've kind of done example 2b before, but we did that in a one-dimensional number line. Now we're doing this in a two-dimensional coordinate plane, so it's going to look a bit different. So let's try this. So I mean, you know, x and y are here, and so if I'm graphing this, I'm going for, basically you're graphing the line y equals -1. Okay, you're basically graphing this is called the boundary line for this inequality. All right, and then you just have to pay attention to the inequality sign. So if you have greater than or less than, when you graph your boundary line, it's going to be a dashed boundary line. Okay, and if you have greater than or equal or less than or equal, okay, you're going to have a solid boundary line. All right, so again, what's a boundary line? Boundary line is this right here, the line where the region of solutions ends. Okay, that's the boundary line. So back here we're basically going to graph y equals 1, but because it's greater than only, we're going to have a dashed line when we do the graph. Okay, so y here, x here. Where is y1? Y is 1 over here, and as we said before, this is a horizontal line, but now because it's y greater than, not greater or equal, just greater, this is a dashed line. Okay, here, and basically you're saying which numbers for y are bigger than -1. Oh, I'm sorry, I made a mistake there. It's -1, so I'm actually graphing down here, forgive me. So I'm down here. Okay, there's -1, and so you're asking yourself which values for y are bigger than -1. Okay, so of course those are all the values up here. So when I shade, when I want to find my solution area, when I want to shade, it's the points above this line. Now usually if you have your equation in slope-intercept form, y is isolated on the left, like this example here. It's simple. If it's y is greater than, you shade above the line. If it's y is less than, you shade below. If you're confused by that and you don't understand, that's why we did the previous example. You can test a point. So if I want to know, do I shade on this side of the line or do I shade on this side of the line, that's why you need to be able to find a solution, an ordered pair solution to an inequality. So for me, I understand that y greater than -1 means I'm shading above -1. Okay, but if that's confusing for you, you can test a point. So we can test a point. Let's say I suspect the solution area is here, so I can take this point and substitute it. So if you do that, this point is 0, 1. Okay, so 0, 1. I can substitute that in here and see, is that a solution? So y is 1. Okay, so I substitute 1 greater than -1. Is 1 greater than -1? There's no x, so I can't substitute x. Okay, so I substitute the y value for this ordered point. Is 1 greater than -1? The answer is yes, 1 is greater than -1. So this works. So this is a solution. Okay, this ordered pair here is a solution to the inequality, and so therefore I know that this is the area that I'm shading. So let me switch to a little highlighter here. Okay, and so this is the area that I'm shading. Okay, So basically what I'm saying here by shading this area is that all the points that lie in this shaded area here, all the points that lie in the shaded area are solutions to this inequality. Okay? Again, the boundary line is dashed, it's only greater than, so points on the boundary line are not solutions. But everything else here in the shaded area are solutions to the inequality. Alright? Okay, so let's try that for x is greater or equals to negative 4. Again, x, y here. And so x is greater or equals to negative 4. Negative 4 is back here. Okay, so here x is negative 4. And now, remember, we're actually graphing the associated boundary line, x equals 4. But in this case, I have greater or equals, so my line is going to be solid, not dashed. Okay, and so x is equals to 4 is a vertical line, and in this case I'm going to do it this way. Okay, let's do a black line. There it is. Okay, it's a solid line. It's a solid line. X is greater or equals to negative 4. X equals 4. Here's the line. Now I want to shade. Again, you can test a point. Okay. For me, these two examples are very, very simple because you're looking for numbers on the x-axis that are bigger or equals to negative 4. So negative 3 is bigger than negative 4, negative 2 is bigger than negative 4. So for me, that's a simple thing. I'm shading this side. You can test a point again. In this case, let's say you can test the origin. Okay, you can say pick the point 0, 0, plug it in here and test it. All right, so basically you take this x value here and you say, is 0 greater or equals to negative 4? The answer is yes, 0 is greater or equals to negative 4. This is a solution, so therefore this point is in my region of solutions. So when I'm shading, okay, I know that I need to shade on this side here. Okay, and so go ahead and shade that, and so this area here is my solution area. Okay, so all the points that lie in this area here are my solutions. Now actually you can't actually go over your boundary line, but so yeah, any point in this shaded area is a solution to this, and in this case, because the line is solid and because it's greater or equals to, all the points on the boundary line are also solutions to this inequality. Okay, so this is a picture of all the solutions to the inequality x is greater or equals to negative 4. Alright, hopefully you understand the whole idea of a solution area, a region. Okay, and so let's talk about two variable inequalities and graphing those. Okay, so there's basically 3 steps that you need to do. First is, before you want to think about graphing the inequality, solve the inequality for y, put it in slope-intercept form. Alright, and just a recap there, slope-intercept form is y equals mx plus b. Okay, then graph the boundary line, and like I said earlier, use a solid line for greater than or equal or less than or equal, and use a dashed line for less than or greater than. Okay, and so you graph the boundary line and then you shade. So basically exactly what we just did above, but now we're in 2 variables. Okay, and so this lays it out very well here. Shade the half plane above the line for y is greater or equal. Shade the half plane below the line for y is less than or equal. So that's the way I approach this. I think this is very, very simple and logical. Once you've put it in slope-intercept form, you've graphed your boundary line, then shading becomes very easy if you have it in slope-intercept form. Greater than means shade above, less than means shade below. Okay, and so let's do that. Let's try that. So step 1 is write the inequality in slope-intercept form. This is already slope-intercept form, so I'm done. Now I can just identify the slope and the y-intercept, graph the boundary line, and shade. Okay, so again, slope-intercept form is y equals mx plus b. So I know my m in this case is 2, and I know my b is 3. Okay, and so we know slope needs to be a fraction for you to graph it easily there. So rise over run 2 over 1, and y-intercept is 3. Alright, so if I do that, let's do xy here. My y-intercept where I start is 3, okay, and my slope is up 2 over 1. Up 2 over 1. Alright, now before you draw the line, look at the inequality. We're going to draw the boundary line, but the inequality here is y is less than. Okay, not less than or equal, just less than. So if it's less than or greater than, like one of these, like both of these examples here, okay, then it's a dashed line. So I'm drawing through these points a dashed line. Okay, there's my boundary line. This is the boundary line. So that's what I graphed here is the boundary line. Now to graph the inequality, I need to shade a region. So again, very, very simple here. Y is less than mx plus b, or 2x plus 3, means shade below. Okay, y is less than means shade below. So that makes this fairly straightforward. If you're putting your function in slope-intercept form first, then you don't really have to test points, because less than means shade below and greater than means shade above. So that's basically all you have to do. If you are confused, you can go pick a point here in an area that you think is the solution region and then test the point. Okay, so you can go and substitute an ordered pair in here and test it. But it's not really necessary once you've got the equation in slope-intercept form. Again, less than means shade below, greater than means shade above. Alright, so you just have to make sure you do your math correctly when you put them in slope-intercept form. Alright, so let's try another one. So step 1 is put your inequality in slope-intercept form. This is not slope-intercept form, this is standard form. So I need to first change this equation into slope-intercept form. You are experts at that by now, so I'm just going to go through that quickly. Okay, and if you do this, just be careful. Things that trip students up is when you divide by negative, this inequality switches. Okay, you have to flip it around because I'm dividing by negative. So just make sure this becomes positive 1/3 x minus 2. Okay, so there's my inequality. My slope is 1/3. The y-intercept is -2, and I'm graphing this. Okay, so -2 for the y-intercept down here. Here's x, here's y, and then slope is 1/3, so up 1 over 3. Okay, fairly different slope. This is still y is less than only. Less than, not less than or equal, just less than. So my line is dashed. Okay, so through these points, let's see if I can do this line justice here. Okay, you're drawing a dashed line. Alright, this is called the boundary line. Okay, and then I'm shading. Y is less than means shade below. Done. I don't have to test points because my equation is in slope-intercept form. Okay, y is less than just means shade below. Simple, straightforward. Okay, so this region is the region of all the solutions, of all the points to this inequality. Okay, all right, so let's do let me do letter D. You can do letter C. Please do that on your worksheet. Okay, you can try that as independent practice, but it's very similar. I'm going to do letter D because that's a greater than example. Okay, and so in this case, again, step 1, solve it, put it in slope-intercept form. So let's do that first. Okay, so I'm getting something like this, and divide by -2 both sides. So remember, I'm dividing by negative, so this has to switch. Okay, and so my slope becomes 5 over 2x plus 2. Okay, so slope is 5 over 2, and my y-intercept is 2. Alright, so again, same idea. going to graph this. B is 2. Okay, and slope is up 5 over 2. Okay, so up here. Again, this is greater than, so it's dashed line. This example here is less than or equal, so this would be a solid line. Okay, but this example again is a dashed line because it's only greater than, so I'm drawing a dashed line here through these 2 points. Okay. And now the reason I did this example is this is y is greater than 5 over 2x plus 2. So greater than means shade above, all right? So in this case, above the line is over here, below the line over here, okay? So I'm shading above the line, all right? And that's the business. So this shaded area here are my set of solutions to this inequality, okay? Or this inequality, both the same thing. Okay, so this shaded area, not the points on the boundary line, but this shaded area or the set of all the solutions to this inequality. All right, please go ahead and try this one. It's a little bit different because it's less than or equal, so it's a solid line, but the principles are exactly the same. All right. I threw this one in here. Your textbook didn't really have this in the examples, but I threw this one in here because you should know how to do this. They had one of these questions in the homework, and I think it's important for you to know how to do this. So this is the opposite. This is not graphing an inequality. This is, if you're given an inequality graph, can you write the equation that matches this, okay, that satisfies these solutions? So basically, I'll do both of these with you. So it's just like writing an equation of a line, but in this case, you're dealing with a region of solutions, so you need to consider that it's an inequality, okay? So let's write the equation of the boundary line first in slope-intercept form. So again, I'm going for this, okay, y equals mx plus b, and I labeled these points clearly for you here, so it's not very difficult to find this information. The y-intercept in this case is -5, okay? So my b is -5. And the slope, I labeled 2 points nicely here so you can find the slope up 2 over 1, okay? Just be sure you're checking the scale of the axes, all right? But these are all 1 unit squares. So the slope is up 2 over 1. So rise 2, run 1, okay? So this is my slope, all right? And so you're just substituting this in, y equals 2x minus 5. But that's not the answer to writing the inequality. This is an equation. This is the equation of the boundary line. We want to write the inequality, okay, that's associated with this boundary line. So the inequality would be the same thing, but you have to come up with your inequality symbol. So in this case, I've shaded above. We've shaded above the line, so it means y is greater than. But it's not just greater than, because this is a solid line. As you can see, solid here, dashed here. So this is a solid line, so it's y is greater or equals to. Okay? So the inequality that gives you this region for a solution is y is greater or equals to 2x minus 5. Right? So solid line, solid boundary line, greater or equals. It's greater than because we were shading above the line here. All right. So here, let's take a different approach. Let's start with the inequality part first. It's the same idea, but I just want to do it a little bit differently. So here we've shaded below the line. So we know that the inequality for this would be less than, and it's a dashed line, so it'll only be less than, not less than or equal to. Okay? So the inequality symbol for this region of solutions here, this inequality would be less than only. Okay? It's dashed, it's not less than or equals to, and it's shaded below the line, so it's only less than. Okay, it's not greater than shade above. So again, simple here, we found that b on the graph here is -2, okay, this point here, and the slope is up 2 and over 4. Okay, so slope is up 2, rise 2, run 4. Okay, so the slope is a half. So I have this information. I can write the boundary line equation very quickly, equals 1/2 x minus 2, and now just apply your inequality symbol. This is a region, this is an inequality. We're trying to write an inequality, not an equation. So just change the equality symbol to the inequality symbol. So this is the inequality that would yield these solutions. Y is less than 1/2 x minus 2. Okay? I hope that's clear for you. And then we were working with absolute value functions in section 2.7. We did transformations of absolute value functions. So you're a champion at understanding absolute value functions. So here it's just graphing absolute value inequalities, not equations, inequalities. So again, very, very similar idea. Your absolute value equation forms the boundary of the graph. Okay, so it's exactly the same thing as for lines, but now we have absolute value function. So you're graphing the absolute value function, the equation, just like you used to, but it's a boundary. Okay, so the absolute value function makes a boundary for a region of solutions. So it's the same idea. So let's just use the same principles we used to graph this. You graph the absolute value function, look at the inequality symbol to make sure if it's dashed or solid, and then you can shade. All right, and so let's look at this. So the vertex here is at, remember the vertex is at HK. So in our example, the vertex here is at 2, 1. Okay, 2, 1. Remember, this is -2, so h is actually 2. This is correct. This is the normal standard form of an absolute value function. Okay, and so here's my vertex 2, 1. All right, so I can plot that point up to over 1 here. 2, 1 over here. Okay, this is my vertex. All right, but now remember how you graph an absolute value function is you use the axis of symmetry. So let me switch colors here. All right, here's the axis of symmetry. If this is the vertex, okay, if 2, 1 is the vertex, then this is the axis of symmetry through the vertex. And now to complete my graph of my absolute value function, you just pick one point, pick one value for x to find a point that's a solution, and then just mirror that across the axis of symmetry. Okay, so just pick any value for x that's not on the axis of symmetry. So usually you just pick 1 over. So if let's say this x value here is 2, I'm going to pick 3. So let's say let x be equals to 3. Okay, now I want to see when x is 3 what's y, so I can find another ordered pair, another point. Okay, so when x is 3, and I just substitute it in here. Alright, so I say when x is 3, I have y equals -1/3 times absolute value of x, which is 3 now, minus 2 plus 1. I substituted this 3 into the equation. And so again, you are very familiar with this because we did it in the previous lesson, but I'll go ahead and simplify this. This is absolute value of 1 plus 1. So basically what you have here is y is equals to -1/3 plus 1. Okay, -1/3 plus 1, and that would actually be 2/3. Okay, -1/3 plus 1 is 2/3. Alright, so my ordered pair is 3 and 2/3. Okay, so that's another point on the absolute value function. So if I go to 3 and 2/3, I'm about up here. Okay, somewhere there. Alright, and so same for the next point. You mirror this across the axis of symmetry. Okay, that's a nice property of an absolute value function. And so now you can draw the boundary. Now I'm drawing the boundary, which is a V-shaped absolute value function. Okay, but this is less than or equal to. So because the equal is there, this is going to be a solid line. So let me see if I can pull this off here. Let me do it in blue. Okay, and so basically a line through that point and a line through this point. Okay, So basically, this is my absolute value function. Okay, so this boundary here we graphed is y equals -1/3 absolute value of x minus 2 plus 1. But it's an inequality that we're actually trying to graph, and so now I need to shade a region again. But this says y is less than or equal. If you understand the principle of less than is below, greater than is above, you'll be fine. You don't have to test any points. We can just go ahead and shade this region. Okay, I'm shading this region. Y is less than or equals to absolute value of -1/3 x minus 2 plus 1. Okay, so this whole region are my set of solutions, including points on the absolute value function. Okay, which is my boundary. All right. Okay, last one, and then we're done. And then we'll talk about this again in class. We'll go over some practice questions. You know, if you have any questions, we'll talk about it. All right. So let's do one more. And this is just a different case where it's greater than, similar principle. Okay. So let's just identify the vertex. Again, you know that the standard form here is y equals a times absolute value of x minus h plus k. So the vertex here is h and k, 2 and -3. Okay, 2 and -3 are my vertex, and so let's do that. Let's plot that point on the coordinate plane. 2, -3 is down here. Okay, that's my vertex. Now let's just plot another point using the axis of symmetry. We can mirror it, and then we have basically our absolute value function. So axis of symmetry would be here. Okay, through the vertex, a vertical line, axis of symmetry. Okay, so let's find another point. So let's look at this, see if we can do this a little bit more intelligently. Doesn't really matter. I'm just going to go for x is 3 again. Okay, what happens when x is 3? So I'm picking one point over from axis of symmetry. So let x be equals to 3, and then let's substitute it into the absolute value equation, not the inequality. Okay, we're just trying to find a boundary point. So let's substitute that. Y equals 3 times absolute value of 3, substituting the 3 in for x, 3 minus 2 minus 3. So y is 3 times the absolute value of 1 minus 3. Well, that gives me 3 minus 3, which is 0. Okay, so my solution, my point here is when x is 3, y is 0. This is a point on the absolute value equation. So when x is 3, y is 0, this is a point on my absolute value function. Okay, on the graph of the absolute value function. And so use the axis of symmetry to mirror this point across the axis of symmetry. Okay, and so now I can just draw my absolute value function. So let's do that. Let me do that in red. Okay, so basically I have something like that and something like this. Okay, so here, oh, I made a mistake. All right, but I'll try and redeem this. So what I did is I graphed the absolute value function, but I didn't consider the inequality. We're trying to graph the inequality. This is greater than, so I've got a solid line right now. That's not correct. It needs to be a dashed line. Okay, so I'll go and dash this after the fact, which is perfectly fine if you're doing this by hand. Okay, so this should be a dashed line because it's y is greater than. And now we can shade without doing a test point. If you want to test a point, fine, you can pick a point here, substitute it and see if it's a solution. If it's a solution, you know you're in the right region. But I understand that y is greater than means shade above the absolute value function. So above the absolute value function in this case is here. Okay, shading above the absolute value function is here. All right, so this region would be all the points that are solutions to this inequality over here. Okay, And that's that. I mean, basically, very similar principle. Absolute value inequality, linear absolute value inequality, absolute value, just linear inequalities as well. Very similar principle. I hope that was clear for you guys. If you have any questions, ask me. Check out your textbook. There's more examples there, and we'll talk more about this in class. Thanks, guys. Have a nice day.